15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on Space Nuts. It's all about astronomy and space science. This is episode 273, believe it or not. And today we're going to be looking at quite a bit. We're going to knock off a whole bunch of questions, but we're also going to be looking at a discovery in regard to a planet that appears to be orbiting three stars, and we can't see it. But we'll look at it anyway. We'll also be following up on the BepiColombo space probe. We've talked about that before. That's the one headed for Mercury, and then it's headed for Mercury, and then it's headed for Mercury, and then it's headed for... but it's made its first pass and taken some stunning photos. I don't know if you've seen them, but very exciting news there. We'll also be chasing up audience questions about the Carina supernova that hasn't happened. Also, the speed of light, the center of the universe, the color of the sky, and a follow-up on something we talked about 4,000 or 5,000 years ago, the TRAPPIST star system, a follow-up question on that we've taken too long to get to, but we will now. Owen, thank you for sending it in. With me, as always, is astronomer at large, Professor Fred Watson. Hello, Fred.
Hi, Andrew. Good to see you again. Looking bright and breezy, as always.
Well, I'm getting excited because it looks like we'll be out of lockdown on Monday, which is only 4 or 5 days away for us. So fingers crossed all goes well. It's been a turbulent political week. We've got new leadership in the state in two of the major parties that are in coalition. So it's crazy time. Crazy time.
Yep, we've got a new minister federally as well.
Yes, we have. Yes, it's all happening. But yeah, we're looking forward to getting back to some kind of normality, whatever the new normal will be from Monday in New South Wales. A couple of things before we start on your topics, Fred. Did you hear that the Russians have sent a film crew to the International Space Station? They're going to do a movie.
Yep.
They've even sent an actress up there.
Well, I didn't know about her, but I did know that they'd sent a film crew up. Yes, okay. Good.
Yes, indeed. So I think that's amazing. I think we talked some time ago about, it won't be long before they're filming movies in space. Well, we weren't far wrong. So that's good. And there's been a milestone achieved by the Chang'e 4 U-2 rover mission on the moon. They've just clocked 1,000 days. 1,000 days.
Remarkable, yes.
Yeah, and still going.
3 years, U-2.
Yeah, 2018, I'm told.
Hard to believe it. Yep. Sounds right.
And
time flies when you're having a good time.
It's been exciting because when they first started, they went, look, we found a rock. And then the other day they went, oh, there's another rock.
That's a rock.
Anyway.
Good, great stuff.
Yes, indeed. Let's get down to business. Astronomers have found a planet that orbits 3 stars. This sounds rare and unusual.
It probably is unusual. It's one of these stories that still is, riddled is probably the wrong word. I was going to say riddled with caveats. I think it's too many metaphors there. Anyway, it's got qualifications, if I could put it that way. So, but yes, it's a star which rejoices in the marvelous name of, I've lost its name, GW something, I can't remember. Hang on, let me find it. GW Ori. GW Ori meaning it's a star in the constellation of Orion. And it means it's a variable star because a star with a name like that, with 2 initials, is a variable star. There's a long story behind that as well. It's 1,300 light years away as the crow flies. And it is a young star which has around it this enormous disk of dust, which is called a protoplanetary disk, dust and gas. And most young stars have this. And it's basically an indicator that planets are being formed. Mm-hmm. However, GW Ori is not your ordinary young star. It's 3 stars.
Wow.
which are mutually in orbit around one another. We've spoken, you and I, Andrew, many times about binary stars, where you've got a pair of stars which are in orbit around their mutual center of gravity, usually called the barycenter. This is the same sort of thing, but with another star thrown into the mix. Now, triple star systems are not rare, but or not particularly rare. They are far less common than binary systems with two stars. But what's unusual is to find one with a protoplanetary disk around it.
Yeah.
But in particular, this disk has some peculiar qualities. First of all, it's two disks. It's it's like a disk, but with an enormous gap in it. And that gap is really significantly big. So it's not, just a narrow gap like the Cassini division in Saturn's rings. It's a big gap. And the really odd bit is that the outer ring is actually tilted in respect to the inner ring at about 38 degrees. It's a significant tilt. So you've got this curious situation of an inner ring, and then at a wonky angle outside it is another ring. And I should mention that these observations come, of course, you might not be surprised to hear this, from ALMA, the Atacama Large Millimeter Array Telescope out there in the Atacama, not far from San Pedro de Atacama. It's a gigantic array of radio telescopes that look at sub-millimeter and sub-millimeter waves. And it's been brilliant at picking up these protoplanetary rings. So the story now switches to an analysis of what can make, what sort of gravitational interactions produce a star system like produce a dust ring like that. And so there are two main camps. One of them, and this is probably where astronomers started, says this curious arrangement of the rings is due to the curious arrangement of the stars in the middle, that it's a triple star. And so you've got really odd gravitational forces involved and curious torques and tidal forces. However, another group, which I think is led by astronomers at the University of Nevada, Las Vegas, if I remember rightly, this group says, no, we cannot make the mathematics work out that gives you a ring system like this from the effect of a triple star system. And so what they are actually basically they're proposing is a planet in the gap. And it's that's pretty strong, actually, strong evidence. They're quite convinced, this team, and I should mention they include astronomers from the United Kingdom as well as the United States. They have really ruled out the idea that the triple star system itself on its own could cause the curious alignment of the dust disk. And so they are left with only the option that there's a planet in there, and maybe more, forming planets.
What would it be like on a planet orbiting three stars, seasonally, and I suppose gravitationally? There's got to be, I don't know if it'd be very comfortable, would it?
No, probably not. Everybody points to Star Wars as the archetypal science fiction movie that featured. In fact, it was two stars, wasn't it?
Two stars, yes.
Yeah, that's right. But I point to something long, long before that, because back in the 1950s, Fred Campson, who was the artist who produced Dan Dare in the Eagle comic, he had a star system called the Three Sons of Loss. And Loss is soul backwards. A lot of his terms were things backwards. The Three Sons of Loss was a triple star system. And so we've got all these lovely illustrations that Frank did of sunrise with the triple star system. Minu, the smallest one, the red star. Anyway, that's just fantasy. I'm just telling you that triple star systems go back a long way in science fiction. And what would it be like? Well, it'd be really interesting. We understand, though, that at the distance where this planet is thought to be from the triple star system, two of them will be so close together that they would look like a single point of light.
All right.
So you'd only see effectively two stars. But you know, can you imagine even that at sunrise or sunset would be just incredible to look at, wouldn't it?
Oh, I imagine so, yeah. I wonder what their seasons would be like.
Yeah, well, a lot of that would depend on the tilt of the planet. I mean, we're talking almost certainly about a gas giant, so there wouldn't be any surface, and it's hard to imagine any life forms on it, although it might form moons, and then moons are possibly a place where life forms could develop. But they would certainly have weird and wonderful seasons.
Indeed, yeah. And we can't see this at the moment, can we? It's all been picked up by radio telescope analysis.
That's certainly the dust disk is. The star itself, the star system itself is visible. I don't know what its brightness is, but the fact that it's called GW Ori tells you it's visible in normal visible light, and it's variable, and presumably some of that variation comes from the fact that these stars slip in front of one another from time to time.
Okay. If you want to read up on that, the study has been published in the monthly notices of the Royal Astronomical Society. So that's where you'll find it.
Yep.
Now, Fred, let's move on to the BepiColombo mission, which we talked about, a while ago now, and one or two times since its launch. And it has just done its first flyby of Mercury, took a couple of selfies and a bit of a video, but the pictures have been quite amazing.
Yeah, Mercury is such a dramatic world, an enigmatic world too, with craters. It looks a lot like the moon at first sight with all these craters, but the missions that have reached Mercury and investigated it, like the Messenger mission, which I think was a NASA mission a few years ago, have demonstrated that it's very odd because it's got this huge iron core, much bigger than you would expect for a planet of Mercury's size. And so there's a lot to learn about Mercury, and that is why this joint European-Japanese spacecraft is on its way there. Its name is BepiColombo, named after a scientist who first suggested the idea of gravitational slingshots. Where you use a planet's gravity to boost the velocity of a spacecraft. And in fact, this is the classic example of that, as you've already hinted at, because BepiColombo has already had one flyby of Earth and two of Venus.
Yes.
And what we've seen now is it was a week ago. So it's the first of 6 flybys of Mercury. And that is all about slowing down the spacecraft to give it a velocity that will match the orbit of Mercury and allow it to go into orbit around the planet. This multiple flyby is a really neat trick, and it's great that the inventor of it is celebrated in the name of the spacecraft.
Can we just sort of revisit the purpose of the mission?
Yes, we can. So it's basically to find out about Mercury. There are 2. It actually carries 2 orbiters, which will be released. I think it's 2024 or thereabouts.
2025, I think.
2025. Yeah. Okay. And it'll be released. Those 2 orbiters will be released to go into orbit around the planet. Obviously, one is studying its magnetic field. It's called the Mercury Magnetospheric Orbiter. That's the Japanese spacecraft from JAXA, the Japanese Space Agency. And the other one is an ESA spacecraft. It is called Mercury Planetary Orbiter, and it basically will look at the surface of Mercury in detail, which is going to be great. We'll see some fabulous images, but also to study the core of Mercury, what I've just mentioned, this extraordinarily large core. And how do you do that? Well, you look at the way the spacecraft behaves under the gravity of this complex planet, because the way a spacecraft orbits tells you about the internal structure.
Okie doke. And of course, yes, as we mentioned, final arrival will be sometime around 2025-ish. That's when they'll slow down enough to catch orbit.
Yeah, that's right. That's the bottom line.
Yeah, all right. There'll be more to come from BepiColombo. After its sixth flyby with those, the photos. We've already seen that. Just like the rover on the moon. Yeah, that's another rock.
Yeah. It is, isn't it? Oh, another space launch. More astronauts in the space station, yeah.
All right. But that's good because it means there's progress.
It means. Yeah.
If things are getting normal, then that's a good thing in terms of space exploration and study.
That's right. I think you're right.
Yes. You're listening to Space Nuts. I'm Andrew Dunkley and he's Fred Watson.
Indeed he is.
Let's take a quick break from the program to tell you about our sponsor, NordVPN. Now, as a Space Nuts listener, you get a special offer from our sponsor. 2 years, a 2-year plan, plus 4 months for free. It's easy to grab the deal. There's a special URL for Space Nuts listeners, so you can jump onto nordvpn.com/spacenuts to look at the deal. First and foremost, it has a 30-day money-back guarantee. Now, if you read the reviews about NordVPN, most people are very, very happy with the service in regard to its speed, its connectivity, and its stability. That's very, very important. And I must confess, I have been using it for a little while now, and I tend to agree. It's got endorsements from Wired, the Huffington Post, BuzzFeed, Forbes, TEDx, the BBC even in England. And it makes your online data unreadable. It protects your personal interests. It protects your browsing. It protects when you're banking and shopping online from cyber criminals and surveillance. And it secures all your devices, regardless of the platform, Windows, Mac operating systems, Linux, Android, iOS. They're all covered by NordVPN. And it gives you access to a global internet service. I mean, if you don't use a VPN, you are basically restricted. You're geo-blocked. This will overcome that. And as I said, there are so many positives, including 24-hour, 7-day-a-week service. So check it out. There's a 30-day money-back guarantee. It's risk-free, and it's 100% guaranteed. And you can get your money back after 30 days if you don't like it. So go to the special URL, nordvpn.com/spacenuts, and find out more. 2-year deal, which will cost you $3.18 a month total, $3.18 a month. Instead of paying over $300 for this service, it'll be $89 for the first 2 years, plus 4 months free. So grab the deal. It's on this URL, nordvpn.com/spacenuts, a special deal for you as a Space Nuts listener, nordvpn.com/spacenuts. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, if you'd like to chat away with other Space Nuts listeners, you can do that through social media, if it's working. The Space Nuts podcast group is on Facebook, and this is where like-minded people, listeners of Space Nuts, can get together and chat, sometimes debate. One of the debates that's come up this week is in regard to something we talked about last week, the legend of Sodom and Gomorrah and this city in the Middle East that they have been digging around and looking at, and some evidence suggests that it was destroyed by an asteroid explosion. That started debate because there's another side of the story that suggests, no, that's all wrong. That's not what happened. So you might want to get in on that discussion. We remain neutral here on
Of course
Space
we do.
Nuts. We are apolitical. But if you do a search in Facebook for Space Nuts podcast group, then you should be able to find the group, join it, and share your photos of your astronomical pictures, or just get involved in the discussions, read the articles that get posted. It's all there on the Space Nuts podcast group. Now, we're going to try and tackle some text questions because the text people do tend to sort of miss out on occasion, which is unfortunate, but we're going to fix that right now. First question, Fred, comes from Patrick in Denver. What are the chances of the primary star Carina A in stellar system Eta Carinae exploding as a pair instability supernova? Wow. If such an explosion occurred when Carinae B was in the closest proximity to A, would it destroy both stars? Great show, and thanks for taking my questions. Good questions too, Patrick.
They're excellent questions.
And I think I mashed up the pronunciation.
No, you didn't. No, Eta Carinii A.
There we go.
So there is the mechanism by which Eta Carinii might collapse to a supernova is still, it's still hypothesized, because we don't know exactly what its mass is. It's likely to be it's likely to be a core collapse supernova, more than a pair instability supernova. These are different mechanisms for the formation of supernovae, and it actually depends on not just the mass of the original star, but its metallicity. That means the amount of stuff other than hydrogen that is in it. Astronomers call all elements heavier than hydrogen or helium, they call them metals. It's a slightly weird and wonderful thing. But
I love
the metallicity,
that word. Metallicity.
Yeah, it's a great. So the metallicity is how much of this stuff there is. The lower the metallicity, the less iron and other elements that's in a star. So I don't know the answer to that, whether it will be basically a collapse to a black hole, a core collapse, or a pair instability explosion. I think core collapse actually doesn't do much in the way of causing a supernova. It just collapses to a black hole, and that's the end of it. Whereas a pair instability supernova definitely does, and that's why the question relates to whether the other star, because it's a binary system, whether the other star will in fact survive that. I can't remember. Was that the question, Andrew? Whether it will survive?
Yeah. The question was: would a pair instability supernova destroy? If it was Carinii A, would it destroy Carinii B if it was close enough?
Yeah, probably. That's the answer is probably. It would certainly. It would certainly have fairly major consequences for Eta Carinii B. And the thing about Eta Carinii is that it is unstable and is thought to be a likely supernova candidate sometime in the astronomically near future, which means within the next million years. But
so how far away is it?
If I remember rightly, it's about 7,000 light years.
Oh, that's far enough.
That's
check. Cool.
It is far enough that we would survive.
Yes.
Rather than be blasted by harmful radiation. There would be radiation. There'd be a neutrino flux, which essentially, would be detected here on Earth. 7,500 light years. I've just been looking. 2,300 parsecs, the astronomer's unit of distance. So we'd measure this neutrino flux, but I don't think it would be life-threatening at that distance.
That's good news. I feel relieved.
Good. Glad you are.
Although, if it happened today, how long would it take for that neutrino flux to?
Well, if it happened today, it would be 7,500 years, because neutrinos effectively start travel at the speed of light. But,
I feel good either way now.
Yeah.
Unless it happened 7,500 years ago and we don't know it yet.
Yeah, well, that's the trick, you see. You don't know. It could have happened already. Exactly.
Yeah, exactly right. All right. Thank you so much, Patrick. Lovely to hear from you. Hope all is well in Denver. Now let's move across to Ohio, and I think it's Randy. Yeah, he says, "Hi guys, thank you so much for a great show as usual." Oh, well, we'll have to throttle back on that, Fred. He said it's great. My question concerns the speed of light, as there's a few things I can't get my head around. What, just you? I think it's everybody.
Yeah. Everybody.
When I turn on my torch, for example, what is the acceleration rate of the photon that is coming out of the torch? And once the photon hits the speed of light, what stops it from accelerating any further? And I'll just bring in the second question before we get back to that. My second question concerns the Big Bang. That's different. I assume that the very singular point where the Big Bang occurred must be at the very center of the universe. If expansion happened in all directions from this point, does that mean there is a singular point in the universe that has never moved or expanded? And do we know where that point is? We'll get back to that. But firstly, the speed of light question. Yeah, you turn the torch on, the photons shoot out and reach almost the speed of light. Can only reach the speed of light in a vacuum, right? And what stopped them from accelerating further?
This is where we get into the real basics of physics, because photons do not accelerate.
They hit top speed instantly.
Yeah, and it's not a photon doesn't go from zero speed to the speed of light instantaneously.
Oh.
It is already traveling at the speed of light when it is created.
Good grief.
Work that one out.
I can't. But the Formula One industry is certainly keen to figure this one out.
Yeah, that's right. Well, so you build a racing car, and when you finish building it, it's already traveling the speed, it's maximum speed.
Wow.
So it's really odd physics. There is a term which is photon acceleration, but it refers to the way the frequency of light changes as it passes through a refractive index that is changing. So this is esoteric stuff. It's a terminology. So photon acceleration in the way that we normally would think of acceleration doesn't exist. But there's an analogous thing with photons, where the frequency of the light changes in response to a change in refractive index. Refractive index is the kind of breaking property of a material. Like light travels more slowly through glass, for example, and through air. It only hits the speed of light that we normally think of, 300,000 kilometers per second in a vacuum. And so that, I suppose, in a way, answers the second part of the question, because if photons, when they are created, they are already traveling at light speed, it means that there's nothing that stops the acceleration. That is the property. It's an inherent property of the photon itself, that speed is associated, at least in a vacuum, with photons. So we don't actually know why it is 300,000 kilometers per second. It's a strangely magical number because, that number is fixed in a vacuum, and as relativity tells you, special relativity, because the speed of light is fixed, space and time must vary, and they warp in response to different things. So it's curious. You would have thought space and time were pretty solid, but actually it's not. It's the speed of light that's solid. And we don't know why it is that figure, but the point is that that speed is an inherent property of a photon.
I think the New South Wales Department of Transport put speed limiters on the photons. I'm pretty sure that law came in.
They do, but there's a proviso that it only happens in a vacuum, and the Department of Transport tends to abhor a vacuum. To use an old quote.
Oh, dear. All right. So that answers the first part of the question. What about the Big Bang? Did it happen in the middle and because everything expanded out at the same time, at the same speed in all directions? So is there a point where the Big Bang was or is or originated? And has it not moved, or is it possibly moving as well? And I think we already know we don't know where that point is. Or we know, but we
do. It's here.
Right. Yes, and that's
here. And if you're on Eta Carinae, it's there. And it's the same everywhere. And that's because this is, the relativistic picture that I'm giving you, the standard model of the formation of the universe. It's because it started in a singularity, which is a point with no dimensions. So if the thing kicks off in a point with no dimensions, and that process makes space, then every bit of space is the same as every other bit. There's no center to it. It sounds like a glib argument, but you have to, in a way, you've got to combine it with the idea that space might be infinite. Because, if space had a boundary, you could naturally think in terms of there being a geometrical center of some sort, but we don't think space is like that. These are huge mysteries. They're things that we really have a lot of very clever physicists putting a lot of very clever thought in it, and there's a lot of very complex mathematical equations that people write. But the bottom line is we don't really understand the mechanics of it.
No, and we don't know how big the universe is. We can only see what we can see, and beyond that, we don't know how much of it there is. So we couldn't possibly define a center because we don't have the data.
Yes, that's right. So exactly. So we can see horizons. There are horizons in the universe beyond which we can't see, and they're all centered on the Earth because it's a horizon. It's our own vantage point on the universe. It's like, if you're plunked down in an ocean somewhere, you've got a horizon, but it's a different one from what somebody else sees who's plunked down in a different bit of the ocean. So you're absolutely right. We don't know the extent of the universe, and therefore we don't really know if it has a center. The assumption is that it doesn't, because it was created from a singularity.
Fair enough. All right. Get your head around that, Randy. And thanks for sending us a question. Lovely to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
Thank you for joining us. And don't forget to visit our website, because there are lots of things you can do on the spacenutspodcast.com website. It's where you can send us questions, whether you want to send them in audio form or text. It's totally up to you. You can check out Astronomy Daily, which is in one of the tabs up the top, to catch up on all the latest astronomy news. And you can visit the Space Nuts shop. Lots of goodies in there as well. Now, Fred, we need to get to our final question. This is a double bunger as well. This comes from Owen, who is in West Cross, Wales. Hi, Nutters. I've always thought that the colour of the sky was due to the wavelength of light, shorter and blue during the day when the sun is directly above, and longer and orange-red during the evening when the sun is setting and moving away. Is this what is meant by scattering? Also, last week, which was not last week, it was probably 14 weeks ago, Fred mentioned in 50 years' time, an observer from the planet in the TRAPPIST star system could see Earth. If this is the case, how are we able to observe the planets in the TRAPPIST system now? I thought it would have been the same time frame observing both ways. Thanks. Love the show. Thanks for the questions, Owen. Let's tackle the light question first.
Yeah, they're good questions from Owen. Thank you, and give my love to Wales. It's a lot to have been there. The question about the colour of the sky and light in the atmosphere is indeed related to a phenomenon which is called Rayleigh scattering. It's named after Lord Rayleigh, who was the 19th century physicist who worked out what was actually happening. And it's what's happening is the particles of light, the photons coming from the sun, in the case of this happens in any scattering medium, but let's talk about the Earth's atmosphere for now. It hits the molecules of air in the atmosphere, and that has this scattering effect. It's basically, it's like 2 billiard balls. You hit one with the other, and it scatters off in some random direction. That's the phenomenon. But what we understand from Rayleigh's work, and it's rock solid, it's not just a theory, it actually works very well, is that the scattering is wavelength dependent. Now, the wavelength of light is what gives light its color. Short wavelength light is blue and violet. Long wavelength light is red. And it turns out that the scattering is very strongly biased towards blue light. So the further towards the blue in the spectrum that your particle of light has, the more it's scattered, the higher the amount of scattering. And by that, I don't just mean the angle. It's physically the amount that the probability with which it will be scattered. So it means that blue light scatters much more readily than red light. And if you want the details, I'll be technical for a minute here, Andrew. The proportionality is 1 over the wavelength to the 4th power, 1 over lambda to the 4th. Wavelength is usually called lambda, and in the formula, it's 1 over lambda to the 4th. So that means that as the wavelength, it probably sounds like I've got this the wrong way round, but as the wavelength gets bigger, it scatters more. It scatters less. Bottom line, because it's a 1 over thing. I'm not making a meal of this. That as the wavelength gets bigger, the scattering is much, much, much less. And the converse of that is, as the wavelength gets smaller, the scattering is much, much, much more. And that's why the sky is blue, because the sunlight scatters the blue and violet light so readily. The violet we don't see because it's blocked really by the transparency of the atmosphere. I'm actually looking at a blue sky now, which is a stunning color, just a deep azure. Actually, I'll look onto a cliff face. Effectively, we've got a very steep rocky slope behind us, and at the top of that, I can just see a beautiful patch of blue sky. So
I just had a look out the window, and it's exactly the same. In fact, I often get comments when I've taken photos, especially that daytime photo I took of the moon recently. People have come back to me and said, "How blue is that sky?" There are obviously people in the world that don't see it like we do.
Oh, that's right, and that's because a lot of places. We have a pretty unpolluted atmosphere generally in Australia, and certainly where you are, Andrew. In regional New South Wales, and it's the pollutants or the dust. Sometimes dust can have the same effect. Dust scatters light in a different way, and if you've got aerosol pollutants in the atmosphere, they also scatter in a different way, and it tends to basically wash out the blue. The blue is just the scattering from air molecules, basically nitrogen and oxygen. So, and that sort of also explains. So, as the sun sets, the light in the sky actually becomes a bit more biased towards the yellow and orange, really, and it's because there's a much greater layer of atmosphere that the sunlight is going through, and so you're seeing. Not just the blue light being scattered, but the green, orange, and red parts of the spectrum are being scattered as well, significantly, because there's so much air there, so much material to scatter, and that's why often when you look at the sun, when it's right down on the horizon at sunset, it will often look quite orange or red because the other wavelengths have all been scattered out. The green, the blue, has all disappeared.
I actually caught a photo one morning before sunrise of the sky, a vivid pink, like the pink of a billiard ball, a snooker ball. It was that pink. It was an amazing photo.
Yeah, that's fantastic. There's one other phenomenon I might mention that's related to this, and that is if you've got the sun really well down on the horizon, right down low, and you have a rainbow on the other side of the sky because there's showers around. Sometimes all you see is a red rainbow. The other colours have gone. Yeah, there's plenty of photos of them on the web. Just a red rainbow, and it looks peculiar because it's a single colour, effectively.
No, the sky is amazing, and I've taken lots of photos of the sky over the years, and particularly catching storm clouds in a sunset that can be just red as red. It's just incredible, some of the stuff we see out here and other parts of the world. It's Yeah, it's quite a phenomenon, and I suppose the ancients, as we tend to call them, would have looked at this and gone, "Oh, the gods are angry."
Yeah, well, that's right. It's got that. Sometimes the sky does look angry.
Yeah, exactly. All right, so that's the colour part of his question answered. Now, going back to our discussion in episode 259 about the observing of planets in the TRAPPIST star system not being able to see each other yet, but in the future, he's suggesting that, well, if we can see the TRAPPIST star system now, couldn't they see us? I got a feeling that's not quite the situation we were discussing.
Well, I can't remember,
to be honest,
but I suspect that Owen is picking up on a bit of Fred Watson skirting around the planet, so not expressing myself particularly well. That is because Rowan's absolutely right. If the light from a star system takes 50 years to get to us, well, our light takes 50 years to get to them as well. It's absolutely symmetrical. I think TRAPPIST-1, the system that Owen's talking about, it's got a proper name as well, Andrew, which I'll give you just to be complete. It's called 2MASS J230629228-0502285.
Okay.
Don't forget that. And that means it's a 2MASS star. 2MASS was the 2-micron all-sky survey, if I remember rightly, which is basically an infrared survey of the sky conducted, it's probably 30, 40 years ago now. It's a long time ago, 30 years maybe. Anyway, it's a cool red dwarf star with, I think, 7 planets around it. So it's a really interesting planetary system. It's thought now, I think, to be 40 light years away. That's the latest value. So indeed, light from TRAPPIST-1 takes 40 years to get to us, and vice versa. Light from our solar system takes 40 years to get there. And I do apologize if I was misleading by probably poor use of words, probably just not being as accurate in my description as I should have been. Naughty Fred.
So does that mean that people on planets around the TRAPPIST system can see us at the moment, if they wanted to, or not?
If they
I think that's where he was getting at.
Yeah. Yes, they can.
Okay.
It may have. I may have been. I can't remember. I might have been talking about. There's some planetary systems which are located in the same direction as the Earth orbits the Sun, the ecliptic plane. And I think we talked about that, about the fact that some of these planetary systems will be able to detect the Earth by transiting across the by seeing the Earth by the fact that it transits across the Sun's disk, and that might be a temporary phenomenon for those stars. But that could be just me misremembering a different conversation. Given that TRAPPIST-1's declination is -5 degrees, that is unlikely. It's in the wrong place for this sort of thing.
Okay, there you go. Thank you, Owen. Great to hear from you in West Cross, Wales. And don't forget, if you do have questions for us, you can log on to our web. You don't have to log on. You just go to our website, spacenutspodcast.com. or spacenuts.io, and just choose your approach to us. The AMA tab gives you the option to send us an email or an audio question, or you can just click on the link on the right-hand side and record your video, record your question there. It's really that simple, as long as you've got a device with a microphone, and pretty easy to get through to us. And we do see them all. We can't answer them all. A lot of the time people actually ask the same questions, sometimes around the same time. I remember a whole bunch coming in that basically covered the same thing. So we can answer them en masse occasionally. So if you don't hear your exact question answered, probably because it's been asked by someone else. That happens. And it's been happening for a long time. Millennia. All right.
Years.
Time to wrap it up for another week. Thank you, Fred.
Pleasure, Andrew. Good to talk. Always
you
good
too.
Fun. Yeah.
Take care. We'll catch up with you next week when freedoms are restored.
Apparently, yeah.
Well, some anyway. All right. Thanks, Fred. Take care.
You too.
That is Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks again to Hugh back in the studio, who pushes all the bells and whistles and blows on the buttons. Or maybe it's the other way around. And from me, Andrew Dunkley, thanks again for joining us on Space Nuts. We'll catch you again next time. Bye-bye.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.